Hello and welcome back. In this video we will look at the graphs of the cosecant function and the secant function. So I think what would be easiest is to remember that the cosecant function is actually the same thing as the reciprocal of the sine function. So what I would like to do is graph the sine function, and then we'll just take the reciprocal of everything that we see in the graph. For the sine function, it comes up to 1 and down to -1, and the important points happen at multiples of pi halves here. So sine function starts at 0, climbs to 1 at pi halves, back down to 0 at pi, down to -1 at 3 pi halves, at 1, and then it repeats this pattern. So we have this wave going on, and it does the same thing back to the right as well, back to the left, and I should have done that. Let's say that will be our sine function in white, and our cosecant function will be in red. And it's going to be 1 over the sine. So let's take a few points and think about what happens at the reciprocal. So at 0, the sine function is 0. So that means the cosecant is 1 divided by 0. That doesn't exist. So we have an asymptote there. But the sine function is 0 a lot. So out here at pi, the sine function is also 0. At 2 pi, we're also 0. And back here at -pi, we're also 0. So we have a lot of asymptotes in here. So let's think about what happens in between the asymptote at 0 and the asymptote at pi. Well, at 1, 1 divided by 1 is just 1. So the cosecant function is going to match that point right there. As we come over to pi, the sine function is getting closer and closer to 0. And if we take 1 and we divide it by a smaller and smaller number, 1 divided by a really small number is really big. So what's going to happen is that we get this little sort of cup right here. And it's going to go off to infinity because we're essentially dividing by 0 there and dividing by 0 there. So we get this little cup action. Well, down here, this is the same shape as up here, but everything's negative. So we get that same shape, this little cup. And this is what the cosecant function looks like in red. And then it would come up. So the cosecant function kind of looks like some sort of like cups coming up, and maybe like what looks like kind of like a mound on the bottom, and it will flip-flop between being sort of on the positive side, being a cup, and then sort of looking like a mound or hill when it's negative. The secant function looks very similar, since the secant is going to be 1 over cosine, and the cosine and sine function look very similar. So let's put the cosine in red, and I'll remember to do this in red this time. So the cosine starts at 1 rather than at 0, like the sine function, and then at we have pi halves, pi, 3 pi halves, 2 pi, -pi halves, -pi, and the cosine function is going to fall down to 0 at pi halves, down to -1 at pi, up to 0, back up to +1. So the cosine function looks something like this. Okay, so our cosine function is in red, and then in white we'll take the secant, which is 1 divided by the cosine. So again, 1 divided by the cosine, well, the cosine is 0 sometimes, and you can't take 1 divided by 0. So we get some asymptotes where our function simply doesn't exist. Everywhere else this will exist. For instance, at 0, the cosine is 1, and 1 divided by 1 is 1. So the secant 0 is going to be 1. As we get closer and closer to pi halves, cosine is going to 0. 1 divided by a small number is a really big number. So instead of going to 0, it's going to shoot off to infinity. And then the same thing will happen down below. With another asymptote out here, and likewise the same thing will happen down here. So the secant and the cosecant look very similar. We've got this sort of bowl and turned over bowls on the top and the bottom, and what you'll notice is that they also repeat. So for instance, the secant, let me do this in red, it's a little bit easier to see. So we have sort of an upward bowl and then a downward bowl, and then it repeats, and we have an upward bowl and then a downward bowl. And how far across is this? Well, this is 2 pi across. The same is the same period as the cosine. Since this is essentially the same function as the cosine, it's just flipped over. So the period is exactly the same. And the same thing happens for the sine. The period of the cosecant is also 2 pi. Another important thing to point out is that the top and bottom, so like the bottom of this bowl happens to be at 1, and the top of this turned over bowl is also at -1. So it's really important to notice that at 1 and -1 is where these things line up here. So let's graph 2 times the secant of 2 theta. So first things first, we know that the secant function is going to be 1 over the cosine. So it's going to look something like this. We're going to have these bowls and these flipped over bowls, and we just need to figure out where they are and how they're arranged. Well, the nice thing about the secant is that at 0 we should be at 1, in the same way that the cosine of 0 is 1. So if I were to plug a 0 into here, what would I get? This would be 2 times the secant of 0. Well, the secant of 0 is 1, and 2 times that is 2. So we know that we're going to have an upward bowl somewhere in here, but is it going to be a really skinny bowl? Or is it going to be, say, a really wide bowl? Okay, so the question is, how can we tell? Well, we know that when we plug in pi halves into the secant, we get an asymptote. So if 2 theta is ever equal to pi halves, we have an asymptote. But that means that theta here is going to be equal to pi fourths. At pi fourths, if you plug pi fourths into this equation, we have an asymptote. So halfway between 0 and pi halves, we have an asymptote. And the nice thing is that the secant function will be symmetrical. So it's going to look like this. And from this, we can continue this pattern on this side. So if we started at 2 and went up, down here we'll start at -2. and we will go down. And then up here at pi, and then down here. And we can begin to sort of imagine exactly what this is going to look like forever. It's the same thing. It repeats. This is a periodic function. So there's our graph. Again, this 2 is just going to stretch this up, or stretch this away from the x-axis. It's going to make everything either further away from the x-axis on top or further away on the bottom. The secant of 2 theta, having a positive number here, is going to squish this down. The period of our function is going to be equal to 2 pi divided by b, where b is this number that we've plugged in here. And since this is 2, this is going to be the period is 2 pi over 2, which is pi. And we can see that this is exactly the case. How far is it from one period? One upward bowl and one downward bowl? That's pi long, and they match. So everything seems to be working fine. Let's do one more example. So let's find the function for the following. So here we've got what looks like a secant or cosecant, because we've got these up and down bowls everywhere. So we know that it's either secant or cosecant. And we can start to identify these guys by looking to see where the asymptotes are. So for instance, we have an asymptote right at 0. This means that we should be looking at the cosecant. And why is this? Well, the secant doesn't have an asymptote at 0. The cosecant does have an asymptote at 0. And this is because the sine of 0 is 0. Can't divide by 0, so we have an asymptote there. So scrolling all the way back down here. So since we have an asymptote at 0, we know that this is not going to be the secant, but it is going to be the cosecant. And the next thing to look at is, where are the tops and bottoms of our, maybe I can do some red, tops and bottoms of our bowls. So here, the bottom of this bowl is at 3, the top of that bowl is at 1. Okay, so what it looks like is we've shifted everything up, right? Because this looks like the bottom of this bowl should normally be at 1, and the top of this bowl should normally be at -1. So we have simply shifted everything up by 2. Okay, so it looks like whatever function we have, we're adding 2 to this cosecant. So I think we had normally called that c. So this is whatever we're adding to this. Also, we can look at the period of this function. So we have one up bowl and one down bowl. And how far across is that? Well, it's pi across. So the usual period is going to be 2 pi, but we might scale it by a factor of b. And if I solve for b here, b is going to be 2 as well. So everything seems to be going well. And then the question is, what is a? So if I'm thinking about all this, and I have a times cosecant of b theta plus c, we know we've shifted the entire thing up by 2. We've squished everything in by a factor of 2 as well. So at the moment, we know that we have cosecant of 2 theta plus 2. But then what about a here? And again, if I were to scoot this down by 2, we would have an exact copy of the cosecant function. So we haven't scaled this up or down at all. There's no stretching in here. So a is going to be 1, and our function is the cosecant of 2 theta plus